Welcome to this channel. In this video, we are going to discuss single time constant circuits. The single time constant circuit implies that if you have more than one energy storing element like capacitors or inductor, you understand these are two energy storing elements. So in a circuit, you may have multiple number of energy storing elements, but if you can reduce the circuit to one energy storing element and one equivalent resistance, that circuit will have a single time constant. Okay, so this capacitor is C, this inductance L. If circuit contains one resistance and one capacitor equivalently, okay, then obviously it is a single time constant circuit. Similarly here also I can have one inductor and one resistance. This is absolutely fine. This is one inductance L and resistance R. It is also a single time constant circuit. So in this case, for both the cases, you can understand that input voltage is suppose Vi, this resistance R, this capacitance C, this is the output voltage V0. We can find a relation between output voltage and input voltage. There we will find one differential equation, and that equation will be first order differential equation, because in across capacitor the voltage across the capacitor is Vc and the current is Ic, and we understand that this Ic relation equals to C dVc dt. Okay, very similarly for inductor, the voltage is VL and current through this one is IL. That time we will consider VL equals to L DIL dt. Okay, these are two basic relations. The current IC equals to C dVc dt, and here VL equals to L DIL dt. With the help of these two, we can find one differential equation to relate the output voltage to the input. Okay, like in the first case, here I can find out this current IC. Okay, now if I apply KVL, Kirchhoff's voltage law, then input voltage Vi equals to voltage drop across the resistance R, that will be IC times R, okay, current into resistance, plus voltage across the capacitor, that will be your V0 or Vc, this much. Okay, that I can write. So this IC I can write C dVc dt, then multiplied by R, then it is your Vc. So this equation, you can see that I can write Vi equals to RC dVc dt plus Vc. So this is one first order differential equation. Here this term is called time constant tau. Tau equals to R into C. Okay, very similarly you will get the first order equation for RL circuit. So if it is Vi, this is your V0. Okay, but here if I consider this current is IL, and for inductor I will consider the parameter IL as a variable. Okay, then we can relate the voltage, it is VL. So now here again I can take KVL. You can see that this Vi equals to the VL plus V0, and VL is your L DIL dt, and V0 is the voltage across the resistance, that is the current flow is IL and resistance value is R, so IL into R. Okay, so I will get one differential equation. From here you will see we are getting one differential equation. So we can rearrange this one. So I can write L upon R. I can divide both sides by R. It is DIL dt plus IL equals to BI upon R. So this differential equation again, the coefficient of this one, this is again your time constant tau, that is your L upon R. So time constant for RC circuit is R into C. Time constant for inductance resistance or a large circuit is L upon R. Okay, so if I have one resistance, one capacitor, or in a circuit, one inductor, one resistance, obviously it is a single time constant circuit. Okay, so we can find the solution for this output voltage. There we will have a particular one solutions. Okay, that thing I have discussed in previous lectures. I don't want to repeat here again. Here the objective is that if circuit includes more than one resistance or more than one capacitor, then the circuit may remain the single time constant circuits. Okay, that one we want to discuss in this video. Okay, now first case, one capacitor or one energy storing element, either capacitor or inductor, any one, and more than one resistance and more than one resistance. If it is like this, that circuit will have a single time constant always. So this is always a single time constant circuit. Why it is so? I'll take one example. Okay, suppose I have this kind of network. Okay, this is the input voltage Vi, this is one R1, it is R2, and this is capacitor C. Now can I reduce this circuit little bit? Obviously we can do, what we can do? We can consider this network. First, we can reduce this thing by its Thevenin equivalent, VTh and corresponding RTh. Okay, that is possible. So we can find 1 VTh, that is the Thevenin voltage, and the Thevenin resistance RTh should be connected in series. So this is the equivalent circuit for the left part. And then I can connect the capacitor, right? So the capacitor was connected here, that I can keep it here. So obviously you can see that this circuit is having one equivalent resistance RTh and one capacitor C. So obviously it's a single time constant network or circuit, and their time constant tau will be equals to RTh times C. So just we need to find out equivalent resistance or Thevenin resistance. That Thevenin resistance times C will give you the time constant. So this is always true. Okay. So here in this case, what is RTh? So how to find RTh? So this network. Okay. So for RTh, the independent source, if it is a voltage source, I'll make it short circuited. If independent voltage, it is a current source, I'll make it open circuited. Okay. So this first thing I'll do, that voltage source I'll make it shorted. Then I look from this terminal to find equivalent resistance that will give you RTh. So in this case, RTh will be the parallel combination of R1 and R2. That looks like that. It's very simple, because whatever current is coming here, that is divided by these two paths, and it will start from here and again it will join here. Okay, they are connected across these 2 points. So RTh is simply parallel combination of R1 and R2, and that is equal to R1 times R2 upon R1 plus R2. Right? So it's so simple. Right? So if this is given, this is your capacitor, this one is 6 ohm, this is your 3 ohm, this voltage is 30 volt, This is your 1 farad capacitor. So what is time constant? So RTH in this case, this 6 and 3 farad combination, 6 into 3 upon 6 plus 3, that will give you 18 by 9 equals to 2 ohm. Okay, so time constant tau is simply RTH times capacitor C. So it is 2 times 1 equals to 2 second. The unit is second. It's done. Okay. Now I'll take one more difficult problem. Okay. Now if this is the circuit, here is the capacitor, like this, and this one source, it could be 15 volt. Okay, now this is suppose 2 ohm, it is 2 ohm, this is suppose again it is 2 ohm. Okay, and this one is 4 ohm, it is 4 ohm, it is suppose also again 4 ohm. Okay, now can you find out? And this capacitor is suppose 3 farad. So can you find the time constant for this circuit? So what to do? So first task is remove the capacitor. So this part you should remove it. Okay, so once you remove this part, then what you will do? So if I remove this one, okay, this part I will remove, and now I will consider this 2 end. So this is A and it is B, and then this voltage source I will make it shorted. So this also I will remove this one. Okay, and I will make it shorted. Then I will try to find out equivalent resistance from these two terminal A and B. Now it looks, because I need to find out RTH. What is the RTH first? Right? The capacitor was, so capacitor was 3 farad, that I said. So it was here only. Okay, this capacitor was there. That I have removed. Okay, so in this case, what I can do? How to calculate equivalent resistance? So you can see these 2 ohm, 2 ohm parallelly connected. That will give you 1 ohm. Similarly, this 4 ohm parallelly connected. Its parallel combination will be half of that. It will be 2 ohm. Then this 2 ohm and this 4 ohm, they are connected in series, one after another. Okay, so can I consider this side? This is your 4 ohm and this is the resistance, it is 2 ohm. So from here I want to consider, okay, and this side, this is your 2 ohm and this resistance is 1 ohm. This is your A and this is your B. Now I can rearrange again. So now you can easily see that these two I can combine. It will give you 6 ohm. These two I can combine. It will give you 2 plus 1 is 3 ohm. Then what I will get? I will get one equivalent circuit between A and B. There, this 6 ohm is here and this 3 ohm will be here. Means now they are connected in parallel. So what is the combination of these two? It will give you RTH equals to 6 parallel 3. That already we have done. It is 2 ohm. So it is 2 ohm. Okay. So RTH is 2 ohm. Thus the time constant tau will be RTH times C. So here it is 2 into 3 equal to 6 second. Okay. So capacitor could be anywhere. But if there is only one capacitor and the multiple number of resistance does not matter. You will get one equivalent resistance RTH, and that RTH you will multiply with capacitor, you will get time constant. Okay, fine. Now if we have more than one capacitor, then how to consider these things? Okay, so next one is more than one capacitor. Right? Suppose, for example, if I consider this thing, okay, this voltage is suppose 10 volt, this capacitor is suppose 1 farad, and this is your 4 farad, okay, and this is your 2 ohm. Can you find time constant for this circuit? Okay, if it is single time constant circuits, first you need to identify whether it is a single time constant or not. Okay, so how to understand this thing? Though it is having two capacitors, but does not imply that it is always second order. Okay, it could be reduced to first order. How to visualize this one? So can I rearrange this circuit or redraw the circuit in this way? This is one capacitor, this is another capacitor. So just I'll flip this resistance and capacitor. I'll draw the capacitor first, this 4 farad, and then I'll connect this resistance R. Here R equal to 2 ohm. Okay, this voltage is your 10 volt. This is your 1 farad. Fine. Now, as earlier I have said that we can simplify the circuit. Now here, can you simplify this circuit, especially this part? So here again we can use one Thevenin. Okay, so VTH we can find out, and it is not RTH, rather C equivalent or CTH, equivalent capacitor we can find out. Okay, so what is the concept? And so what is the VTH and what is the RTH? Can you find this one? So it's corresponding, I can have one voltage, that I'll call it VTH, and one capacitor, I can reduce it to, and then I can connect that resistance here. So this resistance is 2 ohm. So this capacitor is suppose C. Okay, so we need to find out of CTH. So how to find the CTH? Again the same procedure. What you will do? You will just remove this independent source with this 10 volt source. Okay, so this is the capacitor. So this independent source I'll remove it using short circuit, and this is another capacitor here, and we'll look from this terminal, we'll find out C, equivalent C, or CTH I'll call it. Okay, so in this case this 1 farad and 4 farad, they will be in parallel combination. So this is here C1 parallel combination with C2. So in parallel combination you will get C1 plus C2. Okay, so in this case it is 1 plus 4 means 5 farad. So equivalent capacitance will be simply 5 farad. Okay, so once this is your 5 farad, this is your 2 ohm, so time constant will be CTH times R. Means here it's a 5 multiplied by 2 is 10 second. So VTH we can find out. So if you have some curiosity, so how to find this one? You can check that this value could be, this will be the opposite capacitance 1 upon this total 1 plus 4 times supply voltage 10. So it will be your 10 upon 5 means 2 volt. Though it is not useful for us to find the time constant for this circuit. Okay, so if you have more than one capacitor, but it's single resistance. Remember, if it is having single resistance and more than one capacitor, it is always a single time constant. So one resistance like this. So if you have one capacitor and many resistances, okay, then obviously it is one time constant, single time constant. Again, the same thing, if one resistance and many capacitor, that also you will get single time constant. So in this case, the time constant tau equals to that capacitor times R equivalent or RTH. We need to find out equivalent resistance, and in this case the tau should be the one resistance R and equivalent capacitance or this Thevenin capacitance that you can find out. Okay, but be careful, it is Thevenin capacitance. Okay, equivalent capacitance across resistance R. So I'll give you one more example to make it clear, right? So suppose I have this kind of circuit. Suppose here this side I have one source, that side also I have one more source. This is your 2 farad, 3 farad, suppose 1 farad, 4 farad. Okay, and this is your 3 ohm resistance, and it is 10 volt, it is 20 volt. Can you find for this one what is the time constant? So how to find this one? First remove this resistance and try to find out the equivalent resistance from this side, these two terminal A and B. Okay, we can read out this one. So this end is A, this end is B. I have removed this 3 ohm resistance. So there is one capacitor here, here there is one capacitor. Okay, here there is one more capacitor, here there is one more capacitor, and this DC source I'll make it shorted, this DC source I'll make it shorted. And if you look now from this side, then you will get equivalent capacitance CTH. So in this case it is 2 farad, it is 3 farad, this is your 1 farad, this is your 4 farad. So how to find? Now it is very simple. You can understand that these two will be connected in parallelly. So what is that? Equivalently it is 2 plus 3 is, so 2 parallel 3, this is farad, 2 farad and 3 farad parallelly, that will give you 2 plus 3 equals to 5 farad. Similarly this one, these two again parallelly combined, so it is 1 plus 4 equals to again 5 farad. Then this one and this one, they are connected in series one after another, because from this end I have one capacitor, from this end I have another capacitor, and this is your point A, this is your point B, this is your 5 farad, this is again 5 farad. So they are now connected one after another, so it is in series. So C equivalent or CTH will be series of this one, means 5 into 5 by 5 plus 5. Okay, means 5 by 2 farad. Okay, so this is your equivalent capacitance, and C, so this is your C. So what is time constant? C equivalent or CTH into times R. R is your 3 and C equivalent is 5 by 2. So it is 15 by 2, means 7.5 second. Okay, I hope it is clear, right? Now we can consider more complicated example. So I'll take one more example. So can you understand this thing? If I have this kind of circuit, so this is your one voltage source, 10 volt is connected here. This is one resistance R1, it is C1, it is R2, it is C2. This network, is it a single time constant network? Okay. Of course, it is a single time constant. So now how to visualize these things? And why it is so? It will give you first order circuit, always, okay? So you can see that total voltage, this is VI equals to 10 volt. This voltage is your VC1, this voltage is VC2. Okay. Now, one thing you can understand that total voltage VI equals to VC1 plus VC2. Okay. Right. Now, how to find the current and voltage, all the things. Okay. So this total current is suppose I. So this total current I equals to the current through this capacitor plus current through this resistance. So how to find this one? So current through the C1, I can write C1 into d VC1 dt. This is the current through capacitor C1, C dVc dt. And current through the R1, because this voltage is your VC1. So that VC1 by R1. Okay. Again, same current is here. Same current is high again. That is again combination of these two. So can I write it is C2 times dVC2 dt, that is the current through this one, this IC2. And current through R2 will be simply VC2 upon R2, because voltage across this one end is VC2. Right? So this is the equation. Now if you replace this thing in any of this, so this one, there we will get only single variable. Suppose I want to get only VC1. That is possible because C1 dVC1 dt plus VC1 upon R1 equals to C2. Now ddt of VC2, and that I can write. So VC2 I can find VI minus VC1. So can I write VI minus VC1 here? Similarly here also I can replace this part, VI minus VC1 upon R2. So this is one single equation containing VC1 and input voltage VI. So what is the order of this equation? That we need to find out. Okay. So this is your C1 dVC1 dt. It's fine. This is your VC1 by R1. It's okay. And this one I can write this C2 times. Now if it is the input voltage is DC, then obviously it will become 0 here. Okay, I can keep this thing dVi dt minus C2 times dVC2 dt. I can break these things. Plus here also VI upon R2 minus VC1 upon R2. Okay. Now I can combine. Easily I can combine all the things. I can bring this one this side. Again I can bring this one to the left side. I combine with these two. I'll get one equation. Okay. Now how to get these equations? I'll do it here only. Okay. So just I'll erase this part. Just 1 minute. Okay. So how to combine these two? That is very simple. So can you notice that? So this C1 plus C2, these two, this and this, times dVC1 dt. And these two I can combine. VC1 I can take common, 1 upon R1 plus 1 upon R2. Then right side I can keep that simple, VI upon R2 plus C2 times dvi dt. Okay, so this one will give you one equivalent capacitance, C equivalent, and these two will give you one equivalent resistance, 1 upon R equivalent. Can I write this way? So, and if I consider it DC, then I can make it 0. So effectively, what is happening? So this is your C equivalent times dV C1 dt plus this 1 upon R equivalent times VC1, that is equals to VI upon R2. Okay. Now this thing, okay, I can multiply both sides by R equivalent. I'll get R equivalent into C equivalent dVC1 dt plus VC1, that is equals to R equivalent upon R2 times VI. Okay, now you can see this is perfectly one differential equation first order, and we have seen that this part is simply time constant. So this is your time constant tau. Tau equals to R equivalent into C equivalent. So what is C equivalent? Is this addition of these two, C1 plus C2, and what is R equivalent? Parallel combination of R1 R2. Is it right? So it is having a single time constant. So what you will do, this C1 C2 is parallelly connected, so that means C1 plus C2. Again R1 R2 parallelly connected, equivalent resistance is R1 into R2 upon R1 plus R2. Okay, so this thing will be more clear in different way. Also we can find out the time constant more easily. I'll take one more example to conclude this thing. Okay, let me take one more example. Suppose I have this kind of circuit. Okay, this is your source Vi. So this one is R1, it is R2, it is R3, this one is C1, C2. Okay, can you find time constant and whether it is a single time constant or not? My claim is, again, this is again single time constant circuit, only one time constant. So how to visualize this thing? Okay, how to get the time constant value? Okay, now what you will do? So can I rearrange this circuit? So this is the circuit. Now you can see left hand side I have one. I can consider this potential is Vi, this potential again Vi. So why not I'll consider two voltage source instead of one voltage source. That I can do. This side again the same voltage source Vi in repeated way. Okay, it is called voltage source splitting concept. So this end it is connected a pure voltage source Vi, so I can consider this potential is Vi again, this potential also Vi again. I want to find out the equation, system equation, whether it is the first order or second order. Suppose I want to find out the current here, this thing, and that current, this is yours R1, it is R2, this is your R3, it is C1, C2. Now in this expression current I, whether it is a first order equation or second order equation. Okay, if it is first order equation, it is a single time constant. If it is second order equation, it is a double time constant. Okay, right. So what I can do in this case, I can consider Thevenin equivalent circuit for this part, as well as I can go for Thevenin equivalent circuit for this part. Right. So I can have one voltage source VTH1 and one equivalent resistance RTH1. So this is your RTH, it is your VTH1 I am writing. Okay, Similarly, this side, I will have one capacitor and one voltage source. This voltage will be VTH2 and this is your CTH. Okay. So those values we can find out. What is a VTH1? It is potential divider across R2. So it is simply R2 upon R1 plus R2 times V. Or here it is VI. Okay. Similarly, VTH2, what is that? Across capacitor TC2. So in that case, I should consider C1 upon C1 plus C2 times VI. Be careful. Okay. And what is RTH? RTH is parallel combination of R1, R2. That means R1 into R2 upon R1 plus R2. And what is your CTH? Again C1 parallel combination C2, but in this case C1 plus C2. Okay, then I can replace this resistance R3. I can place these things. So I can find out the current. Now you can see this is a single time constant. Two sources are there. Again, these two resistance I can combine, and I have only one equivalent capacitor. So obviously it's a single time constant. So this time constant tau will be this RTH plus this R3, the overall resistance of the circuit, times CTH. So this is your time constant for this circuit. I hope it is clear. So we can discuss more in the other videos. Keep watching. Thanks for watching.